Hello, my name is Ruba Shaban and I'm going to talk about modeling muscle forces from scaled fibers to physiological. A human movement is stimulated by a muscle model, and we know that the muscle contains different muscle fiber which have contractile properties. So every type of muscle fiber has an EMG signal that we can calculate the activation state from. Also, every type of muscle fiber has its own shape and conduction velocity of the motor unit action potential, so we can discriminate slow and fast motor units. EMG signal influenced by muscle fiber length, temperature, and so on. And as we can see here, this is a fast motor units EMG and this is a slow motor units EMG. Muscle models use a hill-type muscle models, and we can represent the activation and deactivation rate with first-order differential equation models, and these two rates influenced by fiber length, velocity, and stimulation frequency. The forces that the muscle produces during contraction using hill-type muscle models. This describes how the muscle force is influenced by its length, velocity, and activation level.
Hello, I am Batul Kharashqa and now I will talk about the developments, application and results. Recently, the electromyographic studies that have been applied on animals showing that there are distinctive frequency patterns in an EMG signal can be distinguished from different muscle fiber types by using the fine wire EMG electrodes that allows for close proximity between the recording electrodes and the contracting muscle. So this figure showing the fine wire EMG electrodes that we mentioned above. As for applications, there was found applications to human muscle. EMG is typically measured non-invasively using electrodes on the skin surface, and this results in the EMG signal getting attenuated in a frequency-dependent manner due to the volume conductor effect through the tissues. There was found some of difficulty in measuring muscle force directly in man. Due to this difficulty, muscle-specific models cannot be directly validated. By using such a frequency information, the recruitment of different motor units have been evaluated, and motor unit recruitment has been shown to depend on movement mechanics. And we have determined optimized wavelets that can be used to measure the EMG intensity from different types of motor units in man. As a first approximation, the transfer functions developed for the GOT model could be used for human muscle, although they may need to be adjusted for activation rates and physiological temperature, and we are need to the force length and force velocity characteristic for human muscle. Gap differential models of the tibia is anterior during running in man result in different force prediction than more basic models with scaled up fibers and signal contractile elements. The challenge will be to validate which models are more accurate. So the results showing that in the future it will be common practice to extract information about recruitment from the information encoded in the EMG signals, then to translate it to activation states of different population of muscle fiber type. And these populations of muscle fibers or motor units can be modeled with a physiologically appropriate within models of muscle.
Hello, my name is Majid Riyad Jazar, and my aim is to compare a hill-type muscle model to a model composed of MUs. A fast elbow flexion performed by only one muscle is considered. The activation necessary for performing the motion and the corresponding frequencies are calculated for cases fast and slow muscles using hill-type model. Then the muscle is modeled as a mixture of 774 MUs with uniformly distributed twitch parameters. So when modeling the control of the human limb motions, the final aim is to estimate the individual muscle forces. The muscle force is usually considered a simple design variable when the external joint moments, calculated by using inverse dynamic approach. To validate the predicted muscle forces, usually processed EMGs are used. That is why the question about the relationship between EMGs and correspondent muscle forces arises naturally. Other approaches are based on hill-type muscle models. The constitutive equations describing this model behavior require data for current length and contraction velocity of the muscle. Knowing the latest individual muscle forces can be computed if the so-called activation parameters are known as functions of time. A fast elbow flexion from a fully extended forearm to a fully flexed forearm with a given duration in a sagittal plane has been simulated. It is performed by one muscle only, named bicep. The used hill-type model is strictly based on the equation given below. Fl is the force-length relationship. Fv is the force-velocity relationship. I and V are the current length and the contraction velocity of the muscle. For muscle model based on MUS, 3 simulations are performed using Motco software. For the first simulation, the muscle consists of 774 MUS that are not separated into slower fast MUS, but their parameters are uniformly distributed from the fastest MU to the slowest MU. It means that the distribution of the maximal amplitude of the MUs, it switches it from 0.558 to 0.06. The contraction time varies from 30 to 80 milliseconds. The half relaxation time changes from 60 to 200 milliseconds, and the lead time varies from 20 to 70 milliseconds. Second simulation, the muscle consists of 774 fast-like MUS, and their parameters are again uniformly distributed. But within other limits, the maximal amplitude of the individual twitches is from 0.39 to 0.23 Newton. The contraction time changes from 30 to 40 milliseconds. The half relaxation time varies from 60 to 100 milliseconds, and the lead time varies from 20 to 30 milliseconds. The third simulation, the same act is done but with different parameters. So, as of my understanding of the article I read, the hill-type model is the most efficient and the most used model of the muscle strength.
My name is Awab Hassan Al-Utaybi, and this is me saying some comments about the modeling muscle forces from scaled fibers to physiological. At first, I am going to talk about wavelets to resolve motor unit activity model. Wavelet analysis considers that each motor unit action potential occurs at a distinct time and leaves a distinct frequency spectrum, which allows us to specifically calculate the time and frequency. Wavelets offer a simultaneous localization in time and frequency domain, which means they are specific and helpful. Wavelets are computationally very fast, and they can separate the fine details in a signal. A filter bank of nonlinearly scaled wavelets is used to analyze electromyography to obtain intensity, time, and frequency information. Coming to one of the most important features about wavelets is that they can often compress or denoise a signal without appreciable degradation. As we discussed before, we know wavelets are important, but although the importance of the wavelets and knowing that they are a powerful tool for signal and image processing, they have some serious disadvantages. The drawbacks of wavelets are shift sensitivity, which signifies the maximum amount of span that will change at any measurement point. 2. Poor directionality. 3. Lack of phase information. And last, And last is that it takes some energy to invest in wavelets to become able to choose the proper ones for a specific purpose and to implement it correctly. About hill-based muscle modeling. Hill-based muscle modeling is one of the most used models to describe the mechanism of force production. The activation and deactivation rates are represented with first-order differential equation models, which means they are not complicated and easy to be dealt with. Models the forces that a muscle produces during a dynamic contraction. Hill-based muscle modeling includes three main parts: contractile element and two nonlinear spring elements. The contractile element is strongly influenced by hormones, stretch, and influences from the motor neurons. The two nonlinear spring elements, one of them is in series and the other one is in parallel. The contractile element includes an active force. The active force of the contractile element comes from the force generated by the actin and myosin cross bridges at the sacromere level. It is fully extendable when inactive, but capable of shortening when activated. And now I'm going to talk about the drawbacks of hill-based muscle modeling. Hill-based muscle modeling do not account for the history dependency of the skeletal muscle force production, which is the effect of the recent contractile conditions of muscles on the produced force. We thank you for listening to us.